Hi everyone. In the previous video, I introduced Gauss's law, which says that the flux through a closed surface is equal to the charge enclosed within that surface divided by some constant epsilon naught. And I also showed you different ways of simplifying that electrical flux equation, which we have really introduced as some integral of the electric field vector dotted with the small area vector. But I came up with some basic rules for how we can simplify this equation to make it a lot more palpable. So for example, if we have a constant electric field and a constant area vector, then we can simplify this equation to the electric field times the area times the cosine of the angle between those two vectors. Now in this video, I'd like to go into how we actually pick our surfaces such that we can use this simplified version of the equation. In the previous video, I was talking about a plane of charge, like just a little surface of charge here. Let's say that we've got a bunch of positive charges kind of distributed and floating around on this metallic surface. The first thing you always want to do when you have something like this is to draw out the electric field and see what it's going to look like. Thinking about, so if you've got a bunch of positive charges, you're going to have an electric field kind of pointing out from that surface directly until you get to the edges. When you get to those edges, you're going to start to see some odd results of arrows pointing out in kind of all directions, including this side as well. Now in the previous video, I drew a Gaussian surface that surrounded this entire sheet. Let me make it three-dimensional here, because the Gaussian surface has to be three-dimensional. But you might start to see some issues brewing now that you've drawn these electric field lines that causes us not to be able to use our simplified equation. So let's extend these lines out and see what I mean. So these lines will extend nicely out into the surface and create a nice perpendicular to the surface electric field line. In this case, the angle would be 0, and therefore we could use EA as the electrical flux through that spot. But as I extend these lines over, you may notice that suddenly that angle is not nearly as constant anymore. And it kind of means that we have broken down. We can't actually use this equation in our simplified version as we were hoping to. And this surface is actually way worse, even if you look at it. The angle is changing throughout the entire surface, and probably even the strength of the electric field is changing through that surface as well. So what I drew for you was actually not a very good Gaussian surface to use for this specific situation. I'm so offended I'm going to erase it even. So let's talk about what are the rules that we need to follow in order to create a good Gaussian surface. Well, there's three that I tend to go with. First of all, it has to be a closed surface. Second, the electric field has to have a constant strength through that surface. If the strength is varying, then suddenly we can't use this equation anymore. The last thing is the electric field has to have a constant angle through that surface. In this case, we were talking about how the angle was changing through the surface, and therefore we couldn't use it. And generally speaking, we want that angle to be 0 degrees or 90 degrees because it makes this equation super simple. So how do we do that with our sheet of charge? Well, let me show you a trick. If you were to create a surface that was significantly smaller than the sheet itself, it pierces the surface at somewhere in the middle. But you might notice something interesting happening with the electric field lines of that smaller section. Let me even blow this up just a little bit so we can look at it more closely. Let me even draw the sheet of charge that's kind of piercing, that we're piercing through this surface, like that. So there's our charge here. Now, because we are zooming in on our tiny bit of charge, all of the electrical field lines are very happily coming directly out of that surface. And we are suddenly no longer seeing those weird edge effects happening. We're only seeing lines that are both up and down, and none of those weird sideways lines that we were kind of getting into with these edge effects. By making our surface a lot smaller and looking at a smaller section of our sheet, we'll notice that the lines are going to be at 0 degrees, or in the case of this surface, about 90 degrees. So we can completely count or discount the electric flux. The only thing that gets a little crazy is that now instead of looking at the entire charge, we're looking at a very small section of the charge that we have pierced with our box. So there's some math tricks that I'll get into in the next video that we can do to deal with that. But for now, we have a Gaussian surface that is happy and obeys all of our rules such that we can use our simplified flux equation. Once you have this set up, then you can actually begin your Gauss's law problem. There are 6 steps that I tend to take when I'm doing a Gauss's law problem, and they're the following. Number 1, first, I draw the electric field, including all of the edge effects. Number 2, I choose a Gaussian surface. I just try to draw it on top of things and see what happens. Number 3, I look at that surface and ask myself, does it obey my Gaussian surface laws to create a simplified flux? Number 4, I ask how much charge is actually inside of my surface. And again, you might actually have to calculate this because it's generally not the entire charge within the surface, it's just some subset or some smaller amount of charge. Number 5, I look at the surface and I find the flux through each of the different surfaces and I add them together to create the net flux, the total flux through that whole Gaussian surface. And then number 6, I solve. I do the algebra required to find the things that are unknown and solve for that unknown. All right, I'd like you to try problems number 2 and 3 and meet me back in the next video, please.